denk ik. Deze waarschijnlijk. Zet even aan. Hier even aan. Die staat aan. Die ringtone. Nou. Mijn geluid doet niks. No. No.
Zit je al met koptelefoon en HDMI?
Oh, het komt uit mijn koptelefoon natuurlijk en dat ding hoor je niet als je op afstand zit. Dat zou het kunnen zijn. Ik vergat inderdaad dat de koptelefoon niks laat horen als je op afstand zit.
Kan zijn dat die geluid over HDMI aan het zenden is in plaats van naar je koptelefoon?
Ja, moet ik ook nog gaan kijken. Luidspreker, sorry, digital. Nee. Hoe doet dat ook alweer? Windows HDMI. Ja, ik hoor hem. Ja. Do you hear a replay? Again, do you hear a replay? Yep. Mooi. Oké. Nice. Sorry, computer audio. Do you hear a replay? Okay, well, let me see what the sure says. Oké. Ik ga gewoon even testen. Misschien hoor je me zo meteen over de andere kanalen.
Oké, succes.
Jo, later.
Hoi.
Oké, zo. Nieuwe poging, nieuwe kansen. Oké. Dan kan ik hier nu geluid aanzetten. Goedendag. Eens even kijken. In theorie zou ik nu geluid moeten horen. Of weet je echt, de rest zou geluid moeten horen. Hello everybody. Does anybody hear any sound? If so, please reply in the chat. Testing for sound. Let's try again. Can you hear me? Okay, that one is obvious. What is this? Okay, is this any better? Oh, wait, I can't hear you. Let me see. Okay, this is a new attempt. Connected to audio. That sounds good. But can you hear me now? I don't think so. Perhaps this works better? Can you hear me now? Oh, I can't hear you either, why not? Yeah. Okay, perhaps this works. Wait. No, Martin was calling me. So you hear me?
I still can't see you.
Okay, I apparently need to do something with the volume. Okay, well that can go later on. Can you still hear me now?
I can hear you, yeah. Can you hear me?
Yes, I can. It's working now.
See me?
Just looking at the sound level somehow. But it seems alright. I have your screen,
Can you see
or at
me,
least
Ed? Can you see me?
I can see you, yes. But my camera is apparently not detected by Zoom, so...
Yeah, you have to go into the settings. Are you using Mac?
Sorry. Let me see.
Are you using a Mac, Edwin?
Let me see what my volume has to say about it. Oh, wait. Okay, that's weird. Okay, my microphone is now at full volume. Participants. I have more participants, it seems.
It's just me and you. And you're recording me.
I heard someone else talking in Dutch. That's a weird thing. Because I don't have... No, I hear you talking. But there's also someone else. Well,
Will someone have to let us into a meeting?
let me see. There's... Well... Okay, now, well, there should be... I have the sound. There's someone else talking here. Where is that coming from? Oh, wait.
Sure. You sent me the right link?
I'm calling Martin, see what he has to say. Hola. Ik probeer wat...
We kunnen jou goed horen, Gary niet.
Oh, ik ben op dit moment te horen?
Je was te horen, ja.
Ja, ik was even te horen. Ik hoor Gary heel zachtjes hier.
Juist.
En ik hoor nu andere stemmen uit de laptop komen, uit mijn geluid komen in ieder geval.
Wat zei je?
Ik hoor andere geluid lijkt wel, alsof er iets Nederlands doorheen komt.
Zie ik. Is Tom er bij?
Ik heb hem net gebeld. Ik heb toen wel dus ik heb de stream key, daar was ook iets verkeerd, die heb ik gecorrigeerd. Ik hoor Gary zelf ook heel zacht.
stapel.
Gary, can you put your microphone in some more sensitive?
No, I'm doing what I always do. I've been using
Okay.
this all day. It's been
Well, I can just connect you to the stream and see how, if the stream, if your voice is audible good on the streaming.
Yeah. Well, I mean, are you streaming video too?
No, I'm not.
I'm assuming that I get to have PowerPoint slides and show those and all that stuff. I don't know what you guys are doing here.
Perhaps I can join Martin in on it. Martin, can you join in the Zoom?
Ik heb Zoom, ja. Wat ga je daar doen?
Well, participants.
Yeah, I was assuming I would do this like every other Zoom, which is where I can control the screen and show slides
Mm-hmm.
and that stuff. Is that what you guys are expecting?
Wacht even.
Wait, I'm trying to. Yeah, that would be.
Maar je video werkt niet, hoe kan dat nou?
Gmail. Okay. Why can't I?
Maar wat is Tom?
I don't get it. There's something.
You guys tested this before? Okay. Whatever. It's supposed to be starting. Hey, Martin. Hi, Martin.
Ah, Martin.
I see you.
There's some calls.
Is your audio working, Martin?
Gain of shirt from mixer. Oh wait, I hear some shirt from mixer.
Now I can hear you. I don't know where it is.
I can see you, yes, but my camera is currently not detected.
I can hear you.
Okay, I didn't audio. I hear better via the YouTube. They hear Gary very well via the Zoom. Maybe you were listening for YouTube.
Okay, that's weird.
But
Um,
here can,
But if it's alright on the YouTube, let's use that.
Yeah, something's wrong with Edwin's system.
Cam, yeah, the cam is very soft for YouTube. I hear him very loud here on Zoom. You can see him. See a very weird books. Seriously, he's hearing in the background.
And that's not a fake background. Check that out. That's real.
Oh, let's not say anything. No, this name is fake, deep fake video.
I am talking.
So what is our plan?
Okay. Yeah, the guy who actually owns the material, the equipment.
We've kept you waiting for far too long, so I'm just going to say, Gary, please take it away.
Okay, I hope you guys can hear me. So let's just start.
We've kept you waiting for far too long, so I'm just going to say, Gary, please take it away. I'm thinking that is a YouTube video that's open somewhere.
So hang on a second. Start.
I'm thinking that is a YouTube video that's open somewhere.
It is. I'm going to stop sharing my screen.
Right, so we have found the YouTube video that was playing in the background. Second attempt. Gary, take it away.
Okay, so hopefully you guys can actually hear me.
So we have found the YouTube video that was playing in the background. Second attempt. Gary,
There's
take it
another.
away.
There's somebody else with a YouTube video going. I'm just going to talk. Let's pretend this is working. I will be working. I'll be talking for about 45 minutes or an hour on this topic, and we'll just start now. So today, a lot of you actually probably know my work in software security. So the background that I'm going to take to give this talk has to do with security engineering and implementation and building security into machine learning. This is important because there's a big difference between using machine learning for security and building security in to machine learning. So this is the security of machine learning. I'm taking a perspective that came from when I retired. I thought it would be fun to take a look at machine learning again and find out what was going on. There's all this hype I'm sure you've all heard about how deep learning networks are capable of doing much more than they had done in the past. And it all seems a little too good to be true. So I thought the way to figure that out would be to look into it from a science perspective. And I put together a group of guys to read papers in the literature. Whoever's doing that, you just should stop. That's just ridiculous. So together with these people, I started reading the literature in machine learning. And of course, because I'm a software security guy, like most of you people, I started thinking about the security aspects from an engineering perspective of this stuff. So ultimately, we formed a group called the Berryville Institute of Machine Learning. Oh God, can you stop those people, Martin? Just mute them or kill them or something. So I started this institute, which has 3 other people in it, and I want to give them credit because the work I'm talking about today, where we have identified 78 risks in machine learning systems, is work that I did jointly with Victor Shepardson and Harold Figueroa and Richie. So I want to make sure that they get credit for the stuff we're talking about. I guess the first thing to do is to make clear what I mean when I say machine learning and AI and deep learning and convolution networks. So I'm going to define some terms very quickly, and hopefully you guys can get a quick overview of machine learning. This is taken from a book by Melanie Mitchell called Artificial Intelligence, A Guide for Thinking Humans. And Melanie said I could use these slides of hers. Back in the 80s, I was doing machine learning research, and I have about 50 publications in machine learning stuff from the old days. And in the old days, AI looked like this. There was a big field called artificial intelligence. A subset of that stuff was machine learning stuff. And an even smaller subset of that was deep learning, or kind of large connectionist networks. Mostly because some of the connectionist technology took quite a bit of computational power to carry out. So from the 50s to the 80s, the field looked kind of like this. Then things changed around 1990 to 2000, and machine learning started being much more popular in artificial intelligence. And in fact, deep learning was still pretty small until about 2000 because computers were still kind of slow and our data sets were not as big as they needed to be. But lo and behold, what happened next around 2010 is deep learning expanded to fill the entire machine learning thing, and that expanded to fill the entire AI thing. And now when you hear popular press talking about artificial intelligence or even machine learning, they really are talking about deep learning, convolution networks, multi-layer neural networks. And so today, when I talk about risks in machine learning, I'm going to be focusing on deep learning networks. And so let's do a quick overview of what that means and where that's coming from. The idea is to use the brain and neurophysiology as a metaphor for a neural network model that learns. And so just in the same way that the brain can take a picture of a dog and it goes through your eyeball, hits your visual cortex, there's edge detection and then simple shape detection in V2 and then complex shapes in V4, and then finally faces and objects in your temporal lobe. Those layers kind of stack up in some sense. You can think of it as a process. And so the idea of convolutional neural network is to have the same thing happen from a metaphorical perspective, where we've got a convolutional neural network that has multiple layers. It's got different layers of neurons, and ultimately it ends up in a classification module that says, oh, that looks like a 85% dog and 15% cat. So what's really important to understand is that the models that we're using, even though they're computationally very, very intense, are definitely just still models, and the neurons are pretty simplistic. Nevertheless, in some convolutional neural networks, like GPT-3, for example, there are literally billions of connections. And so the way we train these things up is we present some input during training, and we get some output out the other end of the network. And if it's wrong, we adjust all the weights all the way back to the input, just a little bit. That's called backpropagation or gradient descent. And usually that works pretty well for these multi-layer networks to train them over time. And it takes millions and millions of cycles of IO pair training to get something to be a good classifier or to be able to do prediction. That's kind of the state of the art in machine learning and convolutional neural networks today, some of those networks do astounding things. Like if you've never played with GPT-3, I would encourage you to go take a look at it, because it's absolutely flabbergasting how great it is at doing stuff. That said, it doesn't really think like a human. And from an artificial intelligence perspective, we're still using pretty darn simplistic models that don't really think. They're just doing auto-associative prediction in a way that is shockingly surprising to humans. So what we thought we would do when we started looking into this stuff is think about security from an architecture perspective. And I want to sort of pause here and focus on that idea, because one of the things that we've been underplaying in software security and application security since the very beginning of the field is the notion of architecture. Some of you have probably heard of architectural risk analysis from reading my books, or maybe you've heard of threat modeling and worked on threat modeling projects. The idea is very similar. The notion is, let's look at the design of these systems and identify risks in the design so that we can then handle them while we're building a working system to use. And so we thought the first thing that we would do while we're doing this scientific work on identifying risks is build a generic machine learning model and identify components in that model, and then think about each of those components individually and separately in terms of risk. So that's the approach that we took. Then, of course, there are some risks that apply to the system as a whole or to multiple of the components that we've identified. That said, these are the 9 basic components that we came up with to describe a typical machine learning model that you come across today in the commercial space and in academic space. Those 9 components are shown here. And in this diagram, processes are ovals and collections of stuff are rectangles. So raw data in the world is a collection of stuff. Data sets are a collection of stuff. Inputs are a collection of stuff. Data set assembly, on the other hand, transforms raw data into data sets. And so that's a process. Given each of these components, we like to think about risks in them and then identify those risks. And we wrote a paper about this last January that is available under the Creative Commons for everybody to download and use for free. If you want to get a copy of the work that I'm talking about today, you can go to berryvilleiml.com, and under results, you'll see an architectural risk analysis paper. So what I'm going to do for the rest of the talk is discuss this risk analysis that we performed at BeNeLux and give you an example of some of the risks that we identified. Like I said before, we identified 78 risks that are kind of equally important to think about in machine learning systems writ large. And what I'm going to do is give you some examples. And in the end, I'll end up going over what we believe are the top 5 risks in machine learning. It's important to distinguish the difference between risks and attacks. A lot of people that are working on machine learning security are focusing most of their attention on attacks. And there's nothing wrong with that. My view is that if you're going to engineer a machine learning system, it's much better to know how to do security engineering and to think about risks that you need to mitigate than it is to think about attacks. And I think that we've seen that as the case in software security as well, where if we teach software architects how to design from a security perspective, then we're much better off than just showing them yet another SQL injection attack or whatever. And so our approach at BeNeLux is very much the same as the software security approach that I think works the best out there in the world. So without further ado, let's spend a few minutes on each of the 9 components in our machine learning model. And I will tell you some examples of risks that we identified, but not cover them all. I think in the end, we're going to be getting exposure to about 20 different risks out of the 78 that we have identified. So you're getting a little piece of the puzzle today, but hopefully a piece that'll help you to understand what we mean when we say risks in machine learning. The number one thing to understand about machine learning, and I think that you probably got this when I showed you my little fake model of a dog classifier up at the beginning of the talk, is that data are absolutely essential to the behavior of a machine learning system. Because in machine learning, you train up the model on a data set and it learns to classify or predict given those training data. What that means is if your data are bad, your machine learning model is going to be equally bad. And so if you're thinking about security in machine learning, you have to pay a lot of attention to data. In fact, they play a critical role in machine learning. And I think about 60% of the risk associated with machine learning models today that are fielded in operational use surrounds this problem of data. So I'm going to spend a fair amount of time talking about that today. There's lots of raw data out there and we can feed it all into our models. And some of those data can be manipulated by bad people because they're public data or they're otherwise not well protected. And so this is an important thing to think about. Let me give you 2 examples of the 13 risks we found associated with this component, raw data in the world. The first is confidentiality. So an ML system that's trained up on confidential or sensitive data, like PII or data that is susceptible to GDPR regulation, for those of you, all of you Europeans listening to this. Those data, if they are used to train up the model, will in some sense be built into the model through the training process. So those data are in the model. And that calls into question, well, does that mean the model is susceptible to GDPR regulation? And the answer is, well, maybe it is. Yeah. In fact, there's a paper we read the other day at BeNeLux. It's actually right here in my pile of ridiculous papers. For those of you who can see this, this is actually written by some people at Oxford, and it's called A Right to Reasonable Inferences, Rethinking Data Protection Law in the Age of Big Data and AI. And it is about how GDPR applies to a trained up system because data plays such an important role. So if you think, well, we'll just use that confidential medical data and we'll train up our machine learning network and then we'll put our machine learning thing over there and we'll keep the data over here and everything will be fine, that's wrong. And in fact, data confidentiality issues are super important because there are a bunch of known attacks that can extract sensitive and confidential information from machine learning systems indirectly through normal use, and they're pretty well known. That's one example of a risk. Another one is that data sources are not always trustworthy or suitable or reliable. So the thing you got to think about when you're thinking about security risk and machine learning is how could an attacker tamper with or otherwise poison raw data? Like, can an attacker get to Reddit and screw around with what's posted on Reddit? And the answer is, oh yes. Well, if we train up our machine learning system on all the stuff in Reddit, what's that going to mean? So, and what happens if input drifts or changes or disappears? Who controls the data? Turns out to be absolutely important for machine learning security. Those are 2 examples of the 13 that we identified in component 1, raw data in the world. There are, of course, 11 more. So let me go on to component 2. This is also around data. One of the challenges in machine learning is that you can't just put raw data directly into machine learning system. You have to transform it into some sort of format that the machine learning system understands and can process. So pre-processing turns out to be absolutely critical to machine learning and thus critical to security. So one of the things we got to worry about is, gosh, what if encoding integrity or other issues can be exacerbated during this pre-processing step, like determining which of the data to pick from out there? And does data pre-processing itself introduce security problems? So bias in raw data processing can certainly impact things like ethical and moral implications. Let me give you an example. If you are, say, an online bank or a old school bank, and you're training up a machine learning system to decide whether or not to give people loans, but your bank used to be kind of a sexist organization, which was also racist for the last 50 years. Things are better now, but the old data are filled with examples of racism or sexism used to deny people loans. Well, then if you train up your machine learning system on all of your historical data, you're going to end up with a racist, sexist machine learning system that does the same thing that your bank did for the last 50 years, which turns out to be bad. So thinking about these integrity issues really, really matters. Another thing that's kind of a dirty little secret in machine learning is that these systems are kind of hard to get to actually work when you first start playing around with them. So the way that you tag and bag or annotate features into your data is really, really important. And an attacker can introduce bias into the system by changing that tagging and bagging situation. In fact, a machine learning system that's trained up on examples that are way too specific won't be able to generalize well. And frankly, much of the human engineering time that goes into making machine learning actually work is spent on cleaning and deleting and aggregating and organizing and just plain old manipulating the data so that it can be used by a machine learning algorithm. People don't really emphasize how much kludging you have to do to make machine learning work, and there's more than you think. So those are two examples of the 8 that we identified in component 2. Component 3 is the data sets themselves. And one thing to know about machine learning systems is that you have to group your data into training set, validation set, test set. Those are different sets. And how you partition your data that you're assembling from the raw data in the real world into those data sets is very tricky, and it deeply impacts future behavior. One of the things that you can do, all first 3 components, raw data in the world, data set assembly, and data sets themselves, can all be subject to poisoning attacks, where an attacker intentionally manipulates data in any or all of 3 of the first components, possibly in a coordinated fashion, to cause the machine learning training to go awry. The notion of poisoning data on its way in might sound a lot like, say, the problems we have in software security with malicious input. And in fact, they are pretty much the same. So the same way we have to worry about malicious input coming into our programs or into our tech stacks or into our networks, we have to do that in machine learning as well. Data poisoning is a real thing. I'll give you an example. There was a famous machine learning system that Microsoft released called Tay, and Tay was supposed to be a Twitter bot. So as soon as Tay got fielded on Twitter, of course, people started screwing around with it. Tay learned very fast how to behave on Twitter by being on Twitter. It was an online system. It adjusted its behavior over time. And what did it learn? It learned to be a sexist, misogynistic troll of a jerk. In fact, Tay was such an asshole that it had to be taken down very, very quickly, and it was quite an embarrassment. And all it did is learn to do what trolls do on Twitter, but it learned it very efficiently and quickly. That's an example of poisoning data going into a machine learning system and ruining the machine learning system itself. Another example is that many systems in machine learning take an old system that's already been trained up on a big problem, and then they do some kind of more superficial, fine-grained training at the end. So you take some somewhat generic capabilities in one machine learning model, you transfer it over here, and you train that up to do something more fine-tuned and specialized training. A transfer attack presents an important risk in this situation where the pre-trained model risks carry over to the new model that's doing the specialized training. The reason this happens in machine learning is because it's expensive to train up a machine learning model. In fact, if we think about GPT-3 put out by OpenAI, it cost about $12.5 million US dollars for that thing to be trained up. And that's a lot of money. And, you know, I can't spend $12.5 million on a machine learning training system. And so what we often do is what we'll say, we'll take GPT-3, we'll start with that, and we'll do some more specialized training and go from there. So risks that were built into GPT-3, like the fact that it got trained up on everything in Reddit, and so it has very sexist ideas about, say, the way women are supposed to behave in the world, which is sort of pathetic, but that's the way Reddit is. It learned that pretty well. So GPT-3 risks can transfer directly into the new stuff we're using. That's 2 examples of data set related risks out of 7. There are 5 more. We get to component 4, where we finally get to the learning algorithm, something like, say, gradient descent, or I don't know, the backpropagation. This is the technical heart of machine learning. This is how we adjust the weights and learn over time. But there's less security risk here than there is in the data. Of course, there is some. The first kind of risk that we identified in learning algorithm stuff is whether or not you have your algorithm online or offline. If your learning algorithm is online, that means your machine learning system continues to learn while it's out there operationally being fielded. In the other situation, offline, you do all of your training first. You train your machine learning system, you test it, make sure it's fine. Then you freeze it and you put it out there for operational use, but you don't continue to learn. Obviously, if you continue to learn, what can happen over time is a malicious attacker can intentionally nudge an online learning system in the wrong direction on purpose. Those of you who may have studied intrusion detection or malicious or anomaly detection in intrusion detection systems back in the 90s will recognize this, because one of the attacks that was identified very early on in anomaly detection systems by Teresa Lunt, who was at SRI at the time, in the NIDES and IDES work, was the idea of moving the operational profile very slowly over attacker land, then carry out an attack, then move the operational profile back to safe land, and nobody will notice because there's no real anomaly there. So this notion of online nudging is an important risk that needs to be dealt with when you're designing a system. Another one is this. If you read the literature in machine learning and you think, wow, that's cool, I would like to run that experiment and see if I get the same results, it turns out that reproducibility is a real thing. Machine learning work has a tendency to be very sloppily reported, even in peer-reviewed technical literature. So oftentimes results can't be reproduced, and that leads to overconfidence in a particular ML system, you know, to perform as it's supposed to. So we might believe that those guys' work really makes it the case that this thing does foobar, but it turns out that we can't make that happen ourselves because there was an important aspect of either the data set or the parameters or the technology that was being used in that paper. And this is a big problem that we're just beginning to grapple with. If you look at the engineering behind most machine learning science today, what you find is a whole series of pretty kludgy stuff, including issues with keeping track of data sets and doing stuff like version control on data sets. The fact that open source repositories are out there available for everybody, but they're not protected by SHA or MD5 hat checksums, sorry, MD5. And these problems of engineering are kind of being swept under the rug because right now we're still in the kind of new science innovation stage, and we're not taking enough of an engineering look at what's going on in the field. So that's 2 out of 11 risks in that component. That brings us to component 5, the evaluation period. The question that we're asking in this process is, when is the training done? Like, I'm training the thing, I'm producing, I'm giving it IO pairs, I'm adjusting weights. When am I done? And how good is the trained model? The evaluation set and the evaluation process is supposed to figure that out. One of the risks that we identified in this component is overfitting. And this has been known for a long, long time in machine learning. A sufficiently powerful machine learning system is capable of learning its training data so well that it essentially builds a lookup table. So, we can give it millions of IO pairs, but it just memorizes them all. And a lookup table doesn't really do you much good, because an unfortunate side effect of that perfect learning is an inability to generalize. So instead of generalizing, the thing just learns a big list and looks it up on the list. We can build that in a Lisp in about 5 seconds. And so, those are things that we have to be aware of. Overfitting was a problem in the 80s when I was working on connection to system, and it's still a problem today. A second example is bad evaluation data. If you have a data set that doesn't reflect the real data that the machine learning system is going to see in the system when it's out there in the world, it might mislead the researcher or engineer into thinking everything's working fine, even when it's not. So the evaluation set can be too small or too similar to the training data to be useful. I can give you an example of that. There's one famous machine learning system that was supposed to distinguish between dogs and wolves. And so it would take a picture of a dog or a wolf, and it would say, oh, I think that's a dog. And if it was wrong, it would get trained and so on. So after being presented with hundreds of thousands of pictures of dogs and wolves, this thing learned to distinguish pretty well between dogs and wolves. And its evaluation set, when they tested it in evaluation mode, it did really well there too. But there was one problem. The data, it turns out, had a problem in them that humans didn't realize, but the machine learning system did. And that was this: every single picture of a wolf also had snow in it. So a little patch of snow would make the machine learning system go, that's a wolf. And it was right every time, because the only examples it had ever seen had that. But when you present it with a picture of a wolf with no snow, it would say it was a dog. So the training set and the evaluation set both turned out to be problematic. And this thing was not a dog or wolf categorization system. Instead, what they built was a snow detection system. That's very classic sort of problem in machine learning that machine learning scientists try to avoid like the plague, but it crops up all the time. Those are 2 of 7 risks that we identified in that stage. Finally, we have the inputs to the model that's being fielded. So the thing is trained up, and now it's out there in the world, and we're putting new input into it. What inputs fed into the trained model during production? And of course, this is very similar to data set assembly risks and raw data risks that we already described. But this is where a certain kind of risk that's getting an awful lot of airplay in the machine learning security business crops up, and that is adversarial examples. So one of the most important categories of computer security risks is, of course, malicious input. And the machine learning version of malicious input has come to be known as adversarial examples. Here's how it works. So you have, say, a picture that you're trying to classify. And if you take that raw data and you overlay it with just the right mask, the picture will still look indistinguishable to a human being. But to the machine learning model, you can make the thing just categorize it as something completely different. I'll show you a couple of examples later. Adversarial examples you might have heard of from the press. The most famous one is probably the stop sign with tape on it that was done at the University of Michigan. And that work is super famous, and rightly so. But the problem with adversarial examples is they've taken up all of the oxygen in the room. And this is only one of 78 risks. It may be the most important one, but there's 77 other risks we got to think about. So knowing what an adversarial example is important, but focusing all of your attention on that is not important. In fact, you shouldn't do that. Another example of a risk here at input level is controlling the input stream. A trained machine learning system that takes its input directly from the outside may be purposefully manipulated by an attacker. Good example of this is a LiDAR system that you have on your car that's supposed to be self-driving car. A lot of your cars today have LiDAR built into them. Well, what happens to a LiDAR system when you light it up with a laser? It ain't pretty. And if you feed those data directly in from an attacker, then you can have all sorts of miscategorization problems in your machine learning. And so the question becomes, who can control those inputs? What can they do to manipulate those inputs? How skeptical should we be of those inputs? What do we do to manage that risk of uncontrolled data coming in the input stream. So that's 2 examples of 5 risks that we identified in the input phase. Component 7 talks about risks associated with a fielded model. So we've got the model done, and now we put it out there operationally, very similar to evaluation risks in many respects. So one thing to think about is improper reuse. We might have an ML system that's used in a transfer situation like I described before. So the risk of transfer outside of intended use is a really important risk that applies here. That is, I meant for this machine learning model to do foo, somebody borrowed it and they're making it do bar, and I didn't anticipate that when I was training it up, but whatever. It's like somebody using a shoe as a hammer. Happens all the time. You know, not the best kind of hammer, but that happens in the world of machine learning as well. Another example that's super important that has gotten a lot of coverage in the machine learning security space, but is unfortunately not being called the right thing, is the notion of a Trojan. So model transfer leads to the possibility that we might put some Trojan functionality into a model, and we put it out there in open source land and people use it, and it has a Trojan built into it and behaves a certain way in certain conditions. This has come to be called backdooring in, unfortunately, in the machine learning literature, where it should just be called Trojan functionality. It's not really a backdoor in the same way that we mean it in security, but that, that's what happens in machine learning. These people are throwing around security terms in a very messy fashion. So Trojan functionality, real thing in component 7. Those are 2 of 5 risks we identified there. There are 3 more. Finally, we get to the inference algorithm itself. So there are more risks that are sort of associated with a fielded model. Here's where output risks really arise. And, you can think about this in a pretty obvious fashion. A fielded model operating in an online way, like we said before, that's still learning, can be pushed past its boundaries. Online machine learning models have a much different risk profile than offline models. And then another example is, in far too many cases, a machine learning system is fielded, but people don't really understand why it does what it does. So then we integrate the machine learning system into a bigger system, and it just sort of kind of works. And that gets into a larger system, and everybody's relying on the machine learning thing to perform the way it was performing before. And then it does something surprising or weird or whatever, and nobody notices. One of the problems in machine learning is that though we understand the math, the machines themselves that we train up are often inscrutable. We don't really know how they do what they do. We don't know what the boundaries are. We don't know what the edges are. That leads to adversarial examples. It leads to all sorts of other problems. But the notion that people that build these things don't really understand how they really do what they do in many cases is a huge problem. Should we rely on them? Well, it depends. Is it a safety critical thing? Is somebody's life going to be ruined if a machine learning system decides that they're subject to recidivism and so they should be kept in prison? Well, yeah. So that's a problem, this inscrutability issue. That's a couple of examples. Finally, we get to the last component, outputs. And, system outputs often the whole point. So we got the machine learning system. We built it to do a thing. We got it out there in the world doing a thing. And obviously, the first thing we can attack is the output directly. So one perfect idea is just do interposition at the output layer. An attacker tweaks the output stream directly. This impacts the larger system that the ML system's integrated into. But, there are a billion ways to do this. And probably the most common attack would just be to do an attacker in the middle attack between the output stream and the receiver. And the real problem is if you do that attack and you don't really know, somebody really doesn't know how the machine learning system is working in the first place because it's inscrutable, you can see that the inscrutability makes this notion of an attacker in the middle attack much easier to get away with. Another thing to think about in terms of risk at this level is ML systems got to be trustworthy to be put into use. And even a temporary or partial attack, like a denial of service attack against a system, can cause trustworthiness to plummet. And so, there's a kind of an Achilles heel right there at output land. It's important that you protect output, that you think about output, and that you don't just report what the ML system says or thinks without really understanding what it's doing. So those are 2 examples of the 7 that we identified at the output level. That covers the 9 components that we took a look at when we were thinking about risks in machine learning system. But then we said, gosh, there's some system level risks that we should identify as well that maybe get beyond or over the component view and happen between or across components. So I'll give you 2 examples of the 10 risks we identified at that level. The first is that many data-related component risks that lead to bias can lead to bias in a machine learning system. And sometimes that bias can be illegal. So machine learning systems that operate on personal data or feed into high impact decision processes like credit scoring or employment or medical diagnosis pose a great deal of risk. When biases are aligned with something like gender or race or age, operating the system might result in some sort of discrimination with respect to that protected class. And there are many, many well-known examples. There was a great one in the New York Times about this thing that was supposed to decide whether or not a prisoner was going to commit another crime, this recidivism thing, and doing facial recognition of people to see if they were previously convicted of a crime. Turns out that that's a hard thing to do. And it also turns out that machine learning systems that do facial recognition are generally speaking pretty good at recognizing white guys, and they totally suck at recognizing black people, and men and women both. And that is a huge problem because, you know, we cannot have a racist system that decides to just keep all black people in jail, though God knows what happens in the United States these days. So that's one example. Another is overconfidence. When a machine learning system that has a particular error behavior, because they always think, oh, you know, 85% dog, 15% cat, is integrated into a larger system, but its output is always treated as high confidence, you can have all sorts of problems because the users might say, oh, the machine learning system's always right, but it isn't always right. And developing overconfidence in a machine learning system is pretty much easier than it ought to be because people don't really understand how they work. So if they're vaguely described and they work most of the time, you might not notice when they're failing catastrophically. And so that's a risk you got to think about, overconfidence. Those are 2 of 10 risks that we identified system-wide. So what I've given you is 20 examples of 20 risks out of the 78 that we identified in the paper. So I would encourage you, if you're interested in our thinking and in what I've described so far, to download the paper and take a look at those risks, the rest of them, you know, because there are a whole bunch more. So the next thing I thought I would do is focus a little bit of attention for the next few minutes on the top 5 machine learning risks. We've already talked about 20 risks, and the top 5 have already gone by, but I'm going to spend a few minutes more on each of these because these are risks that really everybody who uses ML or does security should be aware of when they're thinking about machine learning security. The first is, of course, adversarial examples. And so I thought I would give you some real examples. The pictures on the left are a picture of a bus, a pheasant, and a Mayan temple. The pictures on the right, the rightmost column, looked like a picture of a bus, a picture of a pheasant, and a picture of a Mayan temple. But in that column in the middle is an overlay mask that if you put on top of the bus or on top of the pheasant or on top of the Mayan temple, you can cause a particular machine learning system to identify all 3 of those pictures as leopards. That is an example of adversarial example. So probably the most commonly discussed attack where you fool a machine learning system by providing malicious input, often involving very tiny perturbations, in this case, that mask overlay, that cause the system to make a false prediction or categorization. This is a very important kind of risk. We think it's number 1, but we also think that coverage in the press and out there in the technical space is disproportionately large. So it swamps out all of the other 77 risks that matter just as much as adversarial examples. All right, let's say this one more time. Adversarial examples are important, but they're not the only thing. I hate to say this, but it's kind of like software vulnerabilities. OWASP top 10, important, but there are about 9,000 other things that you can also screw up that are particular bugs. So, you know, over focus on one or two risks and you'll end up protecting only against those risks and not the others. The second most important risk in our top 5 is data poisoning. I've sort of described how this works, but I will remind you that data play an outsized role in the security of a machine learning system. In fact, I think it's about, as I said before, 60% of the risk is kind of hung on data. Are the data screwed up? Can an attacker intentionally manipulate the data that we're training an ML system on? If they can in a coordinated fashion, the whole system can be compromised. Like imagine a system that we're using for target acquisition and, you know, by poisoning the data, we train it to identify tanks as cats. That's not going to be very useful in a military situation. Data poisoning attacks require special attention because we have to focus on the training data and to what extent an attacker can control those data and what they can do to them. And this is there's a thing that most people are not used to thinking about when they're constructing a system. You know, we're used to thinking about that when we operate a system, but now we got to coordinate engineering and operations in a sort of, I don't know, DevOps-y sort of way. Interesting. That's attack number 2, data poisoning. Risk number 3, online system manipulation. I've already described that an ML system is online when it continues to learn during its operational use. So it's modifying its behavior. It's still learning when it's out there in the world. And of course, a clever attacker can nudge the still learning system slowly in the wrong direction on purpose and retrain the machine learning system to do the wrong thing. Sometimes this happens in feedback loop situations too. One example is in the early days of Google Translate, there's a rumor that Google Translate was actually eating its own dog food. So it was taking translations that it made itself and using those as examples of translations that were good. And you can see what happens when you do that. That is no longer the case. Google Translate doesn't eat its own tail. But when it was eating its own tail, it thought it was really good at translation and it was doing some very silly things indeed. So when you can slowly retrain a machine learning system that's out there in the world, that can cause all sorts of security problems. This risk is really complicated because it depends on the machine learning engineers have to consider where the data come from, what algorithm they're using, how they're operating the system. All of those things have to be combined to properly address it. So that's risk number 3. Risk number 4, I've already described as well, but I'll emphasize it again, transfer learning. Because it's expensive to train up really huge machine learning models out there in the world, we have to often reuse models. So we take an already trained base model and we fine tune that to carry out a more specific task. A data transfer attack takes place when the base system is compromised or otherwise unsuitable or whatever, making the unanticipated behavior defined by the attacker. This is like, you know, well-known issue. There's something called bad nets that was published around 2017. Some people did failure modes in machine learning systems in 2019. This transfer learning attack is very much real, and it's something that we're all aware of, but machine learning security people need to really pay more attention to this. As I said before, a lot of people in machine learning reuse already trained up system, start from there. And if you think about GPT-3, GPT-2, those natural language processing systems, a lot of people start with those and just go from there. So all of the risks that those systems drag along apply. Finally, the last of the top 5 risks, and then I'll hopefully have some time to answer some questions if we can figure out how to make that work, is data confidentiality. So data protection, as we all know in security, is really hard. And data protection, when you throw machine learning into the mix, is even harder. So one unique challenge is that if we have confidential data or say GDPR, relevant data. Then we train up a system on that. Through training, they get built into the model. And then the question is, do we have to like subject the whole model and all of its behavior to GDPR now? Maybe we do. Nobody really is sure how to treat that yet. But if you put super sensitive data in your machine learning system, you sure as heck should not just put it out there in the public for everybody to use, unless you want those sub data to be able to be reversed back out of the machine learning model. And there are some really interesting papers now on reverse engineering and black box models. There's one we just read last week in BeNeLux that is about reverse engineering ReLU networks. And oh man, it's just unbelievable the stuff that you can get out of these models because of the linear transformations that they're using. So there are subtle but effective extraction attacks against these machine learning systems. And, you know, data are in there. And so if we can extract those out, it's an important category of risk. That is number 5. So what I've covered so far is an overview of machine learning, the fact that AI has come to mean, say, convolutional deep neural networks, how those things are constructed from a component perspective, how we can hang risks on each of those components and across the whole system, and then how we can extract from our pile of 78 risks the top 5 or top 10. I hope that you've learned some stuff about machine learning today based on that information. If you want to learn more, you can go to the BeNeLux website. There's the URL, berryvilleiml.com. You can send me email. There's my email address. And of course, my website there. I'm really interested in this stuff. I'm doing it just for fun right now. I'm sort of retired. Nobody's really paying me to work on this work. But I find it really, really fascinating. And my view is that all the stuff we're working on in machine learning is going to be relevant, in machine learning security is going to be relevant for the next, gosh, probably 2 decades. So if you're interested in a very fast moving sub-aspect of security engineering, take a look at what's going on in machine learning. We need more smart security people in this space. And then finally, I want to leave you with this message, which may be backwards for all of you geeks out there. I don't know if you can see that. Hopefully you can read it forwards, but you know, stay at home and wear a mask. This is particularly for dumb Americans who have lost power in the United States. We're back to normal. Now I'm going to stop my share and then we'll go back to the Zoom and see what's going on. So thank you for your attention. I hope you found that interesting. Are there any questions? Martin?
Okay. Can you hear me? Okay. Thanks, Gary, for your presentation. And yeah, I know that you're retired, but I don't know what you do. You look younger and busier ever since you're retired.
Well, I'm eating better and I'm exercising more, so that helps.
That must be it.
Yeah.
So, just one question. I think with all that you said, that 87 risk, and there are very fundamental risk in the system.
Yeah.
And what you said, people kind of take what's come out of machine learning for truth and how it is now hyped and used everywhere.
Yes.
What do you think? What is the future? Will it go fundamentally wrong first, or will it be safe enough to continue?
I think it's probably going to be safe enough. I mean, we know about some actual attacks on machine learning systems, like Tay that I explained before. But for the most part, there haven't been a lot of spectacular live attacks yet. So if we get in front of this problem and we anticipate that there will be, then we can do the proper engineering to mitigate those risks. Remember, in any system, the idea is not to get rid of all the risk, it's just to manage it appropriately. And so if we use machine learning technology appropriately and we think about those risks while we're building the systems, we can do a much better job in building systems that are hard to attack or hard enough to attack that we can actually use them. So I think that's pretty cool. And I'm excited about the progress we're making in the field now. I think we've made a bunch of progress. I would like to say this is pretty cool. As soon as we started doing work at BeNeLux, at my little tiny institute, we got calls from Microsoft and Google and Amazon and OpenAI and the Open Philanthropy people, all sorts of groups that are very active in machine learning security. And they've been incredibly interested in what we've had to say, just as we're interested in what they have to say. So there's a very collegial atmosphere in machine learning right now in security, which is great. We're all learning from each other. We're all thinking about these risks and managing these risks. The good news is that the corporations that are pushing this the farthest, you know, like Microsoft and Google, even Facebook, all have dedicated groups that are thinking about security. I do think that it's important that we have outside institutions like, say, BeNeLux, that keep an eye on those corporations and make sure they're not just bullshitting, because we have a track record of a little bit of bullshit out there. And you know, I sort of consider it my job in the world to call bullshit on security baloney coming out of big corporations. I'll continue to do that. And now I've turned my attention to machine learning. So hope that answers your question.
Yeah, definitely. Yeah, you know that how far can we trust them? So one question I got here is like, can we expect an OWASP top 10 for machine learning?
We already published that. We published a BeNeLux top 10. And if you download the paper that I was talking about before, you can take a look at that thing and you'll see it. So so check that out. If you're still on the chat, let me see if I can pull a URL for Berryville and put it up there. If you, let's see, I'm going to copy a link address and place it into the chat, and then maybe you can propagate that to everybody in the meeting, and they can check out the PDF. This is there's a little sign up for that. It looks like a registration wall, but you can lie to it. Just tell it you're Mickey Mouse or Bill Gates.
Yeah, I will add it to the chat after
Great,
this, so that we don't stir anything. Then the other question is there any specific attack targeted to ML chatbots that could be used to compromise or get some information out of a web application to be used in another attack?
Yeah, probably so. I mean, look, these systems are surprisingly good at interacting in a limited domain. So if we could teach them how to do spear phishing, then we could just have an automatic spear phishing thing, and we could automate that faster than we do spear phishing one at a time with humans. There was a paper that was written about GPT-2, which describes some of those risks, and people tried to do that, and they did a very good job thinking about that in GPT-3. There's a woman there named Ariel Herbert Voss who's been doing security for OpenAI, and she's actually participated in a couple of BeNeLux meetings, and we talked to her about some of these risks. They're trying like crazy to identify and mitigate those risks of misuse of technology like GPT-3. But you guys know as much as I do, as soon as we can think up something crazy to do, somebody's going to do it. Like how clever to draw little stuff on my cow. That's really very clever. And you know that it happens because humans are silly, and we can expect humans to behave in silly ways. And if we're going to be serious about it, we have to think about it ahead of time.
Yeah, sorry for that, but
that's okay.
eventually we kicked them out, but
I thought it was funny, but don't tell anybody.
Yeah, okay. Keep it a secret. Okay, let me see. I don't see many questions now, so definitely, I said it's recorded, that it will be reviewed, we'll share it. And thanks for bearing with us, and always great to have you.
Yeah, it was a pleasure. Thanks for the opportunity, and sorry about the technical difficulties. You know, it's okay. These things happen, but next time, test your system before you go live.
It's better than pre-recorded, right?
Yes, and now, my friend, you owe me a cocktail.
Oh, definitely. You will get it. Okay, all. Thanks a lot, and talk to you soon.
Bye-bye.
Stay safe. Bye. Another sessions tomorrow about threat modeling. Wednesday, we had 3 OWASP projects: the OWASP DevLab, the AMAS, and the Cornucopia.
And then we have Thursday Anastasia about cryptography for developers and how do you do it or not do it. So look forward to you and welcome you tomorrow and have a good night. Thanks.